In 2017, a research paper changed the direction of artificial intelligence. It introduced a surprisingly simple idea that would go on to power the systems behind today's LLMs: attention. And in the next few minutes, I'm going to break it down from scratch, as if I'm explaining it to a 12-year-old. So let's start with one problem attention was built to solve. A language model does one thing, guessing the next word. Here, the answer is full stop and the sentence is finished. But how would the model know that? If the model can only see the word mouse, it cannot do that. A mouse might run, squeak, or be chased. The evidence lies further back. A subject, a verb, and now a complete object. Nothing more is needed, so the sentence can end. So the model has to look back, but the question is how? One thing to accept before we start. Every word is stored as a list of numbers, and that list is all model ever sees. Similar words end up with similar lists. This is the whole trick, and it is already done before attention starts. From here on, a column of numbers just means a word. Well, this is a very crucial step where we convert words into numbers, and this is called embedding. And I've already covered this concept in one of my previous video, which is called Building GPT Part 1. So please do check it out if you're having difficulty in understanding this. Now here is the simplest possible way to look back. Add up every word so far and divide by how many words were there. One vector holding a bit of everything. It's simple, fast, and it uses the whole sentence. It is also much worse though. An average is a blur. Cat is 1/8 of that mix, watered down by the, a, and every other filler word. The information is still in there. It has just been smeared out. Averaging treats every word as equally important. But they are not equally important. We want something like this. Most of the attention on the two nouns and almost none on the filler words, breadth and precision. So, where do those numbers come from? They cannot be fixed in advance. They have to depend on the actual words. Working them out for every word and for every sentence is attention. So here's the machinery, and it's smaller than you think. Take one word's list of numbers and make 3 new lists out of it. 3 multiplications. Those 3 grids of numbers are the only thing attention ever learns. Every word gets all 3 and using the very same grids. A question, a label, and something to hand over. Now hold on to those 3. How well does a question match a label? Just multiply them together term by term and add it all up. This is called dot product. Now if they point the same way and gives a big number, that's a good match. If they're at right angles, they've got nothing to do with each other. And if they're opposite, they'll give a negative number. Now apply the same idea in 32 dimensions, where we cannot draw it, but multiply matching entries and add up all 32. One number, saying how much this word wants to hear from that one. Now do that against every word behind it and look at what come out on the top. The 2 nouns. Everything else scored negative. Nobody wrote a rule about nouns. It worked out by on its own. From nothing but the next word came. Now these scores are the raw materials, but 2 problems with them. First, they grow just because the lists are long. So divide by the square root of that length. Second, they are not shares. Some are negative and they add up to nothing in particular. So we use a Softmax function and it fixes exactly that. It makes every number positive and then divide by the total. Now big scores become big shares and small ones nearly vanish. And nothing is exactly 0. Also, that square root is not a decoration. Without it, cat drops from 42 to 19 percentage. The bigger the model, the harsher this gets, until one word takes everything and learning stalls. So we have the shares now, and now use them on the third list. You remember the one each word hands over? So multiply each one by its share, add them together. And this is the whole calculation. And this is the point of the entire mechanism. So a word mouse has been replaced by a new list of numbers, a one that has cat mixed into it. So it's no longer just a word. It's a word in a sentence, carrying the bits of context it decided it needed. So we followed one word, and every word does this at the same time. There's no row we just worked out. And notice the empty half. A word may only look backwards, never at what comes next. The next word is the answer we are training it to guess. If we let it peek, it learns nothing at all, like an exam with answers stapled to the back. 8 words, 8 sets of shares, and 1 multiplication. This is why the whole thing is fast. So here's everything we've built so far, written in the exact way you will see it in the actual paper. Let's read it right to left, in the order we built it. So this means every question against every label. And this division keeps the numbers in range. What about this function? It turns them into shares that add up to 1. And finally, this is the weighted average of what they hand over. And this is the entire idea. 4 steps and 3 grids of numbers it teaches itself. So the question is, does this work? So given that sentence, here is what this head actually predicts comes next. A full stop. The sentence is complete and it knows it. And look, every runner-up is a preposition, which is the only other thing this grammar allows there. It did not just learn the answer, it learned the shape of the rule. But here is the honest scoreboard for this little language. Attention on its own barely beats guessing from one word back. Because there is one thing this head cannot do. It has no idea what order the words are in. A weighted sum does not care which word came first. Shuffle this sentence and it returns the same answer. So tell each word where it is standing. Nothing else changes, and the same mechanism does magic.